Thanks. I will begin. Dear Father, we thank you for this day. Thank you for the students. Just pray you to guide our thoughts today as we survey topology and maybe a little complex analysis, Lord. In your name I pray. Amen. Yeah, I start on time when I actually am doing math. I know. Otherwise, you kind of sense the fact that well, anyway, I won't comment on the other things we do in here. So, topology. What is topology? It's something you'd like to know a little bit about as a math major, right? I know we don't have a course in it here, but on occasion, certain professors will talk about it. But topology is, roughly speaking, the study of continuity. I can't spell continuity. I can't. I also forgot how to spell continuity. Great. Continuity and open sets. All right. Sometimes people will say that topology is just the study of open sets. That's not really wrong, but to make it interesting, it's the study of continuity and what we mean by an open set. I mean, that's pretty much what what's called point set topology is about. So first things first, a definition. And what is it? Oh, really? Yeah. It's fine, whatever. So a topology on a set X, all right, is a collection of subsets, which we'll denote by a cursive T, having the following properties. Number one, you need that the empty set and the whole set are elements of your topology. Number two, the union of elements in the topology are in the topology. Number three, the finite intersection of elements in the topology are in T. All right. So, generically speaking, we say X paired with tau is a topological space. Keep overshooting it. Eventually I'll get it. Any questions? So to emphasize, some structure here, you guys know about power sets, right? So the power set is, this has got to be a subset of the power set of X. So the power set of X would be the set of all subsets, right? So that, of course, includes the empty set and the whole set. So the topology is some subset of the power set, right? So one kind of silly example of a topology, you give me any set, right? And you could say that the power set's the topology, right? Terminology. If U is an element of tau, then U is open. So open sets are the sets which are in the topology, right? And let's see here. On the other hand, if x minus, or set difference here I'm talking about, so if x minus v, in other words, just to be explicit, this is x and x, such x and x rather, x and x such that x is not an element of v. It's my notation, all right? If this is an element of the topology, in other words, if the complement of v is an open set, then v is closed, right? Or it's a closed set. So this is how we define open, this is how we define closed. There's not an epsilon and delta to be seen, is there? Right? Yeah.
But you don't bother stating, maybe on purpose, I'm not sure, in the definition of a topology that the set X is open? That doesn't matter at the point?
Well, no, there is no larger idea of what is open. Like, this is defining what open means. So, now, so I understand your idea. You're saying, shouldn't we make sure that X is an open set in order to make sure that this terminology of topology makes sense? But, I mean, this, by definition, X is open if we're talking about a topological structure on X. Now, you could ask the question, is that consistent with some, if X is a subset of some other space which has another native topology, is that consistent? You know, we'll get to that. That's a good question. But, you know, an example, stupid example, you just take any set you like and use the, you know, topology be the power set, right? This has a name. Do you remember it, Jess?
Well, trivial topology is just X and the set.
So in this, if you have, say, x naught is an element, actually an element of X, right? Then this set, the set just containing x naught, singletons are open, right? Like, any set containing just one point is open in this topology. Give me any subset of your set, it's open. This is kind of annoying, right? But that is a topology. So this is actually called the discrete topology. And I think the reason for that terminology really is because it makes discrete mathematical things open, right? Like, even if you had the lattice, if we looked at the discrete topology in the plane, if I took an integer lattice, you know, like a grid of points, that would be an open set in this topology. So it seems like it's a natural topology to deal with discrete mathematics. That's, I don't know really, interpretations vary. But anyway, there's also an indiscrete topology. What do you think that is? Let's say tau 2. We could call this one tau 1. It's still the same set X. How about this? If you look at just it being the empty set and the whole set, you can run through the axioms. The union of things is in there again. The intersection is always the empty set, or the set itself, right? X intersect X is X. And there you go. It's a topology. So this is called the indiscrete topology. These are kind of extremes, right? If you were to rank them, what would you have? You'd have tau 2, right, is a subset, right, of any other topology you can imagine. And any other topology you can imagine would naturally sort of be a subset of what? This T1, right? So these are extreme examples of openness or not openness, yeah.
That was what we called it in trivial topology.
The trivial topology? It might have. it's been a while, I forgot. But so the terminology here would be that the indiscrete topology is coarser than any other topology, whereas the discrete topology is finer, although I'm getting into murky waters here. But let's go on. Peel off my sticky note. That's done.
You also done stupid topology.
The stupid topology. Let's see here. What I'm worried about is you can come to it's not necessary. There doesn't have to be. The thing I'm about to get confused about is there doesn't have to be like a ranking here. There's for the real line, if you look at the real line, there's different topologies for the real line, which you can't fit one inside the other. Like there's two weird topologies on the real line, both of which are finer than the standard so-called metric topology, which is what we mostly study in courses. And yet you can't compare them. One is not. I mean, they're not subsets of each other, so you can't compare them. I'm getting into the weeds here. Let me go on here. You can talk about a basis for a topology. And so a basis, X a set, a basis for a topology on X is a collection, funny looking D, of subsets of X all right, such that number one, for each X in X, all right, there is at least one, there exists B in B such that X is an element of B, right? So there has to exist at least one member of the basis which contains any point. You pick any point. There's something in the basis which contains the point, all right? And number two, slightly more technical condition here, if X belongs to the intersection of 2, if X is an element of, say, B1 intersect B2, for B1, B2 in the basis, then there exists B3 in the basis, right? And what is the deal with B3? Ah! Lost it. No! So you remembered, Jess? Stupid Moncrief. Moncrief is not stupid. Moncrief is a wonderful book, but it has 70 pages of introductory stuff. So when I lose my place, I really lose my place. Because topology starts like 70 pages into this book. But anyway, B3 has to do what? B3 is going to be a subset of the intersection, right? And what else? X has to be an element of B3. So it doesn't resemble the terminology basis in linear algebra very directly, right? I mean, it's hard to see spanning and linear independence here exactly, but here's why the terminology is in fact warranted. You can build a topology with a basis. How do you do it? The topology tau generated by a basis beta for X is defined as follows. All right. U is an element of this topology if what? For each x in U, right, there exists B in the basis such that what? Take a guess, guys. So we've got U, right? X has to be an element of B. And can B look like this? No. B has to be like that. Actually, he has strictly subset. I don't know. I think that's fine. Yeah. U is an, I'm saying U is an element of tau. U is in the topology if and only if each point in U allows us to find something in the basis. There exists a B in the basis such that B contains the point and that B is a subset of U. So this is a set theoretic generalization of the notion of interior point, right? I mean, it's essentially saying that X is an interior point with respect to the basis, you know? So there's a lemma that follows usually shortly after this, lemma tau generated by a basis beta is the union, well, it's formed by unions from the basis. Let X be a set, B be a basis for the topology X and X, then X equals the collection of all unions of elements of B. Right. Of course, that includes the empty union. Otherwise, we'd be in trouble. Right? So, let's get into a point here, guys. So you could, for the real line, let's talk about that. There's my eraser. I introduced this term basis because it's easier to, the rest of the examples I want to show you are way easier to communicate with the concept of a basis. All right? So the, so here's an example that's familiar to us, X equal to the real line, right? So one thing you can do is you can give it the standard topology. What's the standard topology on R? Basically, you just use open intervals. Open intervals, the usual meaning, right? X in the reals such that what? These form a basis for the standard topology on the reals. Now you may need to take an infinite union to get certain things that are open, like an open ray to infinity is is an open set with respect to the standard topology because it's the union of, you know, here, like if I want 0 to infinity, I can realize that as the union, right? I equals 1 to infinity of 0i, if I like, you know. You can prove that those sets are equal, and since 0 comma I is in the basis, that means that the union of that's also in the basis. So, for example, that's open. On the other hand, if you look at, say, 0, 1, right? And if you look at the reals with that removed, what do you got? You got minus infinity to 0, unioned with 1 to infinity. But this is open by much the same argument. It's not hard to show that that's open. We have the union of open things, which is by definition open, right? Or by construction, if you like. So that says what? Zero, 1 is closed. So closed intervals are closed sets. Not that surprising, but, you know, this terminology is consistent, and yet it can be inconsistent. Let me show you what I mean. Let me take a minute for a weird topology. I think we don't need this anymore. You guys know the definition now, so we're good. I'm trying to give you guys a sampling of the most important terms in topology so that you've got a shot at questions which might be asked in a general math test, right? Okay, so the other, you can use the lower limit topology, so-called lower limit topology. And in this topology, it has the basis with typical elements looking like these intervals. And so those are your, oh, okay. Just making sure it wasn't me. So this forms the basis for what's called the the lower limit topology, which is different, of course, than, right? I mean, this is a non-standard topology on the reals, because, I mean, part of it is that in this topology, you know, this set is open, right? But obviously that's not open with respect to the standard topology, right? It's not closed either, right? This is a set which is neither open nor closed in the standard topology. It's not a dichotomy, right? There are sets which are neither open nor closed. Okay. There's also subbases, but let's not get into the weeds too far here. All right, so that's standard topology. Now, this notion of interval generalizes. It generalizes to what is called an order relation on a set, you know? So this, you can, if you have an ordering, if you have a set, if you have a space X with an ordering, so what's an ordering? It's a simple, or you know, this if X has an ordering, and suppose it's a simple order relation, what's that mean? If I pick, say, A and B from X, what can you tell me about those? Right, either A is equal to B, or A is less than B. You can't, I mean, or B is less than A, right? then I mean that's it. So a set has a simple order relation if you can do this for any pair of elements. And if you have a set with an ordering, then you can construct intervals in the usual way, but for an unusual ordering. All right? We usually say that you can't order points in the plane. You know, like I ask, what's the ordering on the complex numbers? You know, we say, well, you can't order those. Is that true? Well, it's only true in as much as we can't make a nice ordering, but you can give an ordering to C, just not nicely. You do it like this. If I have x1 and x1, well, I'm sorry, x1 plus I, y1, and x2 plus I, y2, you just think about these like letters in, think about it like letters in a name, you know? So if I had like Cook, and I had, you know, Clark, and I asked you which one came first in alphabetization, you immediately know that Clark is less than Cook, right? Because L comes before O, even though C matches up. On the other hand, if I have, you know, Book versus Cook, then you know that Book is less than Cook because the B beats the C, right? It wouldn't matter if we had like this. Oh, that's not a good example. If I had, this was Bazook, if that was a word, this would still be the case, right? Because the B is the dominant thing there. Yeah.
Is there like some sort of theory that exists that says that all sets can be ordered?
Can all sets be ordered? That seems like something that people might have studied, yes. Let's see here. So x1, y1 is less than x2, y2. What are the rules? If and only if what? Either what? Either x1 is less than x2, right? Or x1 equals to x2 and what? Y1 is less than y2, right? What I'm trying to say is if you think of the x and y coordinates like you think of letters, you can put basically an alphabetical ordering on pairs in the plane. And you can decide whether one point is greater than another according to this rule. So I sometimes ask the question, which comes first, 1 or I? Is 1 less than I? I don't know. This is 1, 0. Is it less than 0, 1? Nope. In fact, we can clearly see that I is less than 1, right? Because we've got 0, 1 is less than 1, 0. But why is this useless? This is useless because that ordering doesn't play nice with complex algebra. Like it is in no nice way related to the modulus or to complex number multiplication or anything we're interested in complex analysis. So the fact that there is this ordering is kind of detached from the analysis that you want to do, which is why we just tell students there is no ordering, which is a lie, but is a convenient lie. But anyway, if you have an ordering on a set, you can set up the order topology by just doing this. And it doesn't have to be ordinary less than. Like I can set up an order topology on the plane using the lexicographic ordering of the plane. That would not be the same topology as the one which we are familiar with from other classes. Let's get to that one. You can also talk about a product topology if you have two spaces Cartesian product together. But for time, I will not talk about that. Subspace topology I should talk a little bit about. So if U is a subset, let's say that S is a subset of X. all right, with topology T, then you can talk about the topology of the subspace. The so-called subspace topology is defined as follows. It's just equal to S intersect U, such that U is in the topology of the superset. So this really is in some sense what you were asking about, Alan. If we have a subset in a topological space, then the way we generate a topology that is natural with respect to the ambient space in which it's found, we just take intersections of the subset with the whatever the open sets are in the surrounding space. Now, so for example, the topology we're most familiar with is actually the metric topology. So metric topology is generated from some notion of distance in the space. We say that the sets are open if they're within. Well, we use a basis of open balls is what it boils down to. So like the metric topology, if you have X and you've got a distance function, which is X cross X to the non-negative reals, then the distance function has what? Like the distance from X to X is what? 0, right? What's the distance from X to Y as it compares to the distance from Y to X? I kind of just gave it away, sorry, but I mean, it should be equal, right? It's not like, the time of coming to school versus going back home. So 1, 2, and you also have, the other thing is the distance from X to Y plus the distance from Y to Z, it ought to be greater than or equal to the distance from X to Z. This is the so-called triangle inequality. So if you have a set with these three properties, and also, it's kind of, it's folded into my definition there, but we also need that the distance from X to Y is greater than or equal to 0, right? And distance from X to Y equals to 0 if and only if X equals to Y, all right? That's also part of the fine print here. Positive definite. If you have all of this, then your space is said to be a metric space. This makes X a metric space. Much of real analysis can be done for metric spaces. Metric spaces support sequences, sequential convergence. You can study analysis with sequences in a metric space. Not every topological space can be made into a metric space. In other words, not every topological space is metrizable. One of the deep questions that you study in topology is when it is possible to put a metric on a topological space. If you can do it, though, you can form a basis with the balls, like epsilon balls. Epsilon ball centered at x naught. This is going to be what? This is going to be x in your space, such that what? Such that the distance from x naught to x is what? Less than epsilon. Man, this is really potent. So this is epsilon ball centered at x naught, right? And these form a basis for a metric topology on X. The reason I say this is the metric topology is the standard topology that we use in Rn. Most of what you do in calculus here is about Rn, right? R2 or R3. So in R2 or R3, the metric topology basically uses either open disks, right? This, if we use absolute value, I mean, special cases, of course, the distance between two numbers, A and B, is what? The absolute value of B minus A, right? The distance between two vectors is the norm of B minus A, right? Or if you like, that's the square root of B minus A dot B minus A. Anyway, that's the the length of the vector connecting the 2 points, the length of the displacement vector from A to B. That's the distance function in Rn. And so that reduces to the open intervals for the real line, but it gives you open disks for the plane or open balls for R3, and past that I'm unwilling. But let's think about the subspace topology in view of that, right? So this is why I'm talking about all this, is if I have a subset, say a surface S, right? And it is that's an example of a subset, right, of R3. Then what would the subspace topology on that look like? What's an open set? You got to think about the intersection. There's also a theorem that says if you have a basis, one of the things with subspace topology is if you've got a basis for the superspace in which the subset's found, you can take a basis for the whole space, and it induces a basis for your subspace in a natural way. So, like, to find what's the basis for the open sets in S? Well, I can use the intersection of S with the open balls. So if you look at, it's stuff like that, right? I mean, it ends up being like little curvy open disks. Those form a basis for the open sets in S. Does that make sense? No. For the real line, if you fix your attention on a closed interval from A to B, right, and you want to talk about what is open with respect to the topology on A to B, the subspace topology on A to B induced from the regular, standard metric topology, the subspace topology on the closed interval, you just get from looking at like intersections of open intervals. That forms the basis. So like this would be open, this set would be open, or this one over here would also be open. So you get like half open sets as subsets of A, B, which are open with respect to the so-called subspace topology on the closed interval. So this is important when you're dealing with like restrictions of some object. Often we use the subspace. We use the subspace topology a lot. You're like, I so enjoyed talking about quotients in the last class period. I mean, class before last, right? Is there a concept of quotient topology? In fact, there is. But this I cannot cover in 2 minutes, so I will not talk about it. It takes me a long time to explain quotient topology. It's subtle.
I'm curious about the distance metric. If you can basically find an order for anything, even if it stinks, why can't you get a metric for it also? You kind of hinted at some don't have a metric.
Yeah, well, that's the thing is, if you can find a metric, it implies that the space is what's called Hausdorff. So a Hausdorff space has this property that I think is familiar, If you pick 2 points, say X and Y, right? In a Hausdorff space, there exist open sets, all right, which separate these points and yet do not intersect. That property follows from it being metric, because you can play games with the distance between the 2 points and take subdistances smaller and construct open balls around each point which don't intersect. But in a general topological space, you don't have the Hausdorff property. So apparently you can't build a metric there. But it seems like you ought to be able to, right? Because of that. And like you said, yeah, I know. So it took us a while to work out all the demons here. And some of them still are roaming about. But that's a Hausdorff space was actually next on my list of things to talk about. There is a way of talking about limits in terms of open sets. You talk about limit points and so forth. I'm not going to get into that today. I think we don't have enough time. But what I would like to talk to you about, because we still have time, is the other three big ideas. The one, of course, is, and I won't get the complex analysis today, I'm sorry, but apparently I'm not going fast enough. So sorry. It's okay. We still have next week, right? Yeah, unless you want to go back to quizzes. No? No? So you guys put me to work. So there's other terminology is connected. What does it mean for a set to be? So we talked about open, we talked about closed. What does it mean for a set to be connected? What does it mean for a set to be compact? All right. And what does it mean for a function which goes from, say, a space X to a space Y to be continuous? How do we define those in terms of topological concepts, you know? So I'll do the last one first. So here, we assume we've got some like topology on X. We assume we've got some topology on Y, all right? And F is said to be continuous if and only if, all right, each V in the topology of Y, all right, has F inverse of V in the topology on X. Let me put that into words. What that says is that the inverse image of an open set must be open. So this is a really exotic definition if you think about some things that you probably haven't thought about continuity for before, right? How about a sequence? You guys deal with sequences, right? What's a sequence? Say a sub n. If you think about that as a function, it's a function, what? A goes from what? From n to whatever you're looking at, right? Usually the reals. Think about this. If you take the inverse image of anything in the reals, what does it give you? You know, pick your favorite interval, a to b, whatever. It's some collection of, you know, n naught, n1, whatever. It's some collection of integers. You know, it could be infinite, could be finite, I don't know. But it's a collection of integers, right? So if you use the discrete topology on the integers, that's open. So with respect to this terminology, if we use the discrete topology for the natural numbers, sequences are continuous maps. So if you can prove something about continuous maps and it's a general theorem, it applies to sequences the same way as it applies to polynomials. That's a pretty profound abstraction, I think. But anyway, that's continuity in the abstract, is the inverse image of open is open. You can show that in the context of metric spaces, that reduces to the epsilon delta definition you've been taught. Compact, what's compact? So a compact set has this following property. Every open cover of X has a finite subcover. Yeah. Oh, no. So you might wonder, what on earth is a cover of X? A cover of X is simply a collection of sets. It's a collection of sets whose union gives X. Here, for example, I could take like this these two boxes, right? And I could look at like little rectangles like this, always starting from the corner. Right? And down here, always starting from this corner. All right? So if you think about these subrectangles, the union of all of them forms both of these boxes together, right? That's, well, that's an open cover. It's fairly clear what the finite subcover is in that case, right? You just take the whole box and the whole box, that would be a sub thing of it. This is not, I don't know how to explain that quickly. Well, anyway, that is how to define compact, but the interesting thing is that this compact basically means finite, all right? It means that, for example, in a metric space, if you have a closed and bounded set, so this is interchangeable with closed and bounded for metric space. And maybe more than that, but so for example, if you want to see if something's compact, if I've got something that's got a fuzzy edge, it's not going to be compact in the in like the plane. But if I have like a something like this is compact. Something like this, not compact. If I have a half plane like that, that's not compact because it's not bounded. And I'm talking about compact with respect to the usual Euclidean topology. So compactness is an important idea. Connected means that there is no separation. So a separation would be if I can write x as equal to x1 union x2, where x1 intersect x2 is empty, and x1 and x2 are open. If I could do that, then that's a separation of the space. Like, these are disconnected. So what does that mean in a connected space? A connected space you could also say this is true if and only if the only sets both open and closed are what? So to be open, you have to be in the topology. To be closed, the complement of the set has to be in the topology, right? What's the complement of the whole space? The empty set, which is open, right? So the whole space is closed and open. Likewise, the empty set's complement is the whole space, which is open. So the empty set is closed. The empty set are always both open and closed in every topology. If those are the only sets having that property, if the only sets that are both open and closed are empty set and X, that is another way of saying it's connected. This is often used in proofs, like in complex analysis, to prove that things are connected or not. If you just start sorting through what that means, that's actually just a little set theory proof there. And finally, let me just share with you guys the important, very important theorems about continuous functions and connected and compact things, all right? So the important theorems that everyone should be aware of is that You can also capture continuity by saying the inverse image of every closed set is closed. That's an equivalent characterization of continuity. There's a few others, but that's a big one. And the other thing I was going to tell you, come on. I'm getting there. Come on. The image of a connected space under a continuous map is connected. If you have a continuous function and you feed it an interval, the range of it, all right, the image of it is also connected. That's sometimes very useful. Every compact subspace of a Hausdorff space is closed. It wasn't metric I should have put here. I should have put Hausdorff, I think, because I just read every compact space of a Hausdorff is closed. Although, and then finally, the image of a compact space under a continuous map is compact. So continuous image of connected is connected. Continuous image of compact is compact. Those are kind of easy things to remember for a multiple choice test. And I hope that something I've said comes in useful. I don't know. I'm trying. It's my best of topology there in 50 minutes. I think that. Oh, one last thing. X and Y are said to be, there'd be a for shame not to mention this. If you can find F going like this, all right, and if you can find F inverse, in other words, if F is a bijection, and if both F and F inverse continuous, all right, then we say X and Y are homeomorphic. This is topology's version of isomorphic. Right. This means that they're the same spaces as far as topological structure is concerned. So it's actually really difficult to show that R and R2 are not homeomorphic. If you take a course in topology, trust me, it will kind of weird you out how long it takes to actually prove that. So, I mean, topology is a deep, interesting, and fairly modern topic. I mean, this is really come of age from like 1930 or so in this formalization that I'm sharing with you. It's relatively recent, but by now pretty well established mathematics. So, anyway, I'll shut up. See you guys next week, where we will